Hello everyone,
Not letting
my
me
name is
reply
Johanna
to my
Mathieu
camera
and I'm an
recording.
assistant professor at the University of Michigan. I'm going to present to
Can
you a
you hear
method for ensuring a load aggregator's power deviations are safe for distribution networks. This is joint work with my student, Stephanie Ross. The work was supported by the U.S. National Science Foundation. First, let's discuss the problem and the objective. Third-party aggregators are becoming more common in the US. A third-party aggregator provides services to the transmission system operator by aggregating and controlling resources like electric vehicles and thermostats to provide services like frequency regulation and ramping. A third-party aggregator works alongside a utility operator but doesn't necessarily coordinate with the utility operator. The aggregator partially synchronizes demand on the distribution network in order to be able to follow signals like frequency regulation signals. This helps the transmission system operator in providing balancing to the network, but could hurt distribution network operations, for example, by causing overloads on transformers or voltage problems throughout the network. And here you can see the baseline load versus the controlled load for an aggregation of distributed energy resources. So the question is, how should a distribution network operator and a third-party aggregator coordinate? In this paper, we develop an online method of determining safety constraints for aggregators' control actions. You can see in this figure that the distribution network operator sends safety constraints, in yellow, to the third-party aggregator, trying to provide balancing to the transmission system operator by following an energy balancing signal, in blue. And then the aggregator computes safe control actions, which it sends to distributed energy resources. These are safe in the sense that they ensure that the network does not have any voltage violations or overloads of transformers. While most load control work ignores the impact on the distribution network, there's been some recent work on network-aware load control. 3 examples are shown here. These approaches require the distribution network company to be the aggregator, or they rely on a third-party aggregator having substantial information about the distribution network, which may not be acceptable from a privacy and security perspective. There are a couple of recent papers which tackle the problem of deriving safe control actions. Nazar and Almasaki derive an inner approximation of the safe set of real power deviations at each bus in the network. Future work is necessary to compare the relative performance of their approach and ours. The method proposed by Molzen and Rold certifies whether a distribution network will operate safely under any set of possible power injections. If a network is certified safe, then the control actions by a third-party aggregator will be safe. However, this approach leaves open the problem for networks that cannot be certified as safe. So next, on to the methods. Before defining the safety constraint, I'm going to introduce some notation. On the left, you can see an example distribution network. Real power consumption at each bus is modeled as constant power with 3 components. The first is the deviation in power consumption of controllable loads, delta PC. The second is the baseline power consumption of controllable loads, PC hat. And the third is the power consumption of uncontrollable loads, PUC. Reactive power is defined similarly, and we assume constant power factor loads. On the right, you can see a 2-bus example. The axes show the change in real power injections at buses 1 and 2. The gray set is the actual safe set, and the blue set is an inner approximation that's easier to compute. Alpha min is the radius of the circle. Injections are considered unsafe if they violate one of the distribution network constraints listed in the bottom left: voltage magnitudes, line currents, or transformer apparent power. For a larger network, delta PC is a vector. The bottom right equation is the general form of a safety constraint, which says that the norm of the change in power injections should be less than the norm in alpha min. Then the question is, how do we find alpha min for a large network? The general approach to determining the safety constraint is shown here. We will restrict our attention to ensuring that there are no voltage violations. In step 1, for each bus, we find the minimum sized delta PC that causes an undervoltage at that bus, and then solve a second problem that finds the minimum size delta PC that causes an overvoltage at that bus. This gives us a set of alphas. In step 2, we find the minimum size alpha from that set and call it alpha min. In step 3, we set the safety constraint to limit the norm of alpha min. We'll go through the details of step 1 next. Of the 3 steps shown on the last slide, step 1 is the main challenge. We formulate an optimization problem to find the unsafe deviations for each bus. Here's the formulation that finds the minimum sized vector of deviations that causes an undervoltage at bus M. The objective function and the first constraint are opposing forces on the size of delta PC. The objective function minimizes the size of the deviations, but the deviations must be large enough such that an undervoltage occurs at bus M. The subsequent constraints are the controllable load capacity limits, the constant power factor assumption, the sum of the load components, the nodal real and reactive power balance, and the reference angle and voltage constraints. Notice that we use the AC power flow equations, and so we have a nonlinear, non-convex problem. The problem must be solved for each bus in the network. Additionally, the overvoltage problem must be solved for each bus in the network. And here are steps 2 and 3 again. If the number of nodes in the network is big N, we will end up with 2 times big N solutions. And so in step 2, we find the minimum sized alpha, where here the size is based on the 2 norm. Step 3 then limits the sum of the squared changes in power consumption by the 2 norm of alpha min. We also considered measuring size with a 1 norm. Here you can see the 1 norm version of the safety constraint and objective function. In our case studies, we will compare the performance of both approaches. Now on to the case study. In our case study, we find and verify the safety constraint for a realistic network at a particular operating point, and we compare both the 1 norm and 2 norm methods. The modeling details are shown on the left. We use a 56 bus single phase equivalent model. We assume 50% of the load at each bus is controllable, and we assume the range of controllable load is plus or minus 80% of the baseline power. We solve the nonlinear non-convex optimization problems with IPOpt. On the right, you can see the distribution network we use. The colors show the voltage at each node in the system under nominal conditions. Here is an example of one of the optimization problems we solve in step 1. On the left, you can see how the network voltages change when we change the network injections to force an undervoltage problem at bus 20. On the right, we've plotted the optimal solution of the undervoltage problem at bus 20. The top plot shows the voltages corresponding to the nominal operating point and the voltages corresponding to the optimal solution across all buses. You can see that the optimal solution forces an undervoltage at bus 20. The bottom plot shows the changes in real power that force an undervoltage at bus 20. Note that the largest deviations in power occur at bus 20 and downstream of bus 20. The next step is to choose alpha min amongst all the alphas generated from solving optimization problems in step 1. Here on the right, you can see the optimal objective value for all 2 norm undervoltage problems. No feasible solutions were found for overvoltage problems in the case study. This means that changes in power injections won't cause overvoltages in this network. As you can see, bus 32 has the minimum objective value. So the alpha associated with bus 32 will become alpha min. You can also see here that there's no feasible solution found for buses 1 to 10 or 40 to 56. That means that we can't create undervoltage problems at these buses. Keep in mind that our tool for creating these undervoltage problems are changes in the controllable load, and the controllable load is only a fraction of the network load. Here we compare the 1 norm and 2 norm methods. On the left, you can see a plot of the solutions to the undervoltage problem for bus 20. The top plot shows the 1 norm results, and the bottom plot shows the 2 norm results. The 1 norm results, the ones in purple, show that the solution concentrates the changes in power injections around the buses close to bus 20, while the 2 norm solution shows that the changes in power injections are spread out amongst the buses. In this case study, the 2 norm safety constraint allows the aggregator a larger balancing capacity. But in general, we can't say whether one approach is more or less conservative than the other. We next verify the safety constraints. On the left is the verification of the 1 norm safety constraint. On the right is the verification of the 2-norm safety constraint. Let's look at the plot on the left. The purple dashed line shows the 1-norm safety constraint. Specifically, we are plotting its 1-norm objective value. The blue dots show the solutions to the 2-norm undervoltage problems, but specifically we're plotting their 1-norm objective value. When those points are above the purple dashed line, it means that the solution is unsafe. When they're below the purple dashed line, it means the solution is safe. The plot shows that all solutions to the 2-norm undervoltage problem are correctly categorized as unsafe by the 1-norm safety constraint. Similarly, on the right, we can see that all solutions to the 1-norm undervoltage problem are correctly categorized as unsafe by the 2-norm safety constraint. This verifies that both constraints are accurate. The paper also derives conditions under which an optimization problem can be eliminated from the set of problems that are necessary to solve. We apply these conditions in a case study and reduce the number of problems to solve by 89% for the test network and 67% for a different test network with capacitor banks installed. This is important as it makes the approach much more computationally tractable. In conclusion, we have designed safety constraints to limit a load aggregator's control actions to ensure a safe network operation. The approach is privacy preserving in the sense that the distribution system operator computes the safety constraint given its private information, and the aggregator adheres to the constraint without revealing its private control algorithm. However, the approach is also conservative. The safety constraint is conservative by design, and it excludes some power deviations that are actually safe for the network. In terms of balancing capacity, the case study suggests that the 2-norm safety constraint may allow for a larger balancing capacity than the 1-norm safety constraint, but this isn't necessarily always the case. In future work, we will try to extend the problem to a 3-phase unbalanced power flow setting, and additionally relax the non-convex optimization problem to provide a guarantee of safety. If you have questions about our approach, feel free to ask now, or you can contact me at jlmath@umich.edu. Thank you very much for your attention. Okay, well, thank you. Sorry about that. I had really hoped to have a live presentation. You can hear me now, right? You can hear me. Okay, so we ended up listening to my voiceover on my PowerPoint, which I used to do my video, but I didn't think it was worth troubleshooting in the limited time we have. So I think I've stopped sharing now. So anyway, I know that I was sort of talking over myself at the beginning, but this is joint work with my student, Stephanie Ross, who now works at the Brattle Group. She got her PhD in January, and so she wasn't able to give the talk. So I hope I can answer your questions, and if not, I'll defer to her and follow up with you later. So I see that there's already some questions in the Q&A. So I'm just going to open those up, and I think everyone else can see those as well. So Brian is asking, might this generalize to PV and storage? Yes, absolutely. We just considered the flexible capacity of the loads, but you could consider it's agnostic to what kind of distributed energy resource that you're looking at. How could you adjust step 2 to allow changes in Q rather than constant power factor? So that's just a function of modifying the ACOPF that we're solving so that you don't couple the two of them. And then you potentially could look at, so some way to model the resource that you're interested in to link P and Q or allow them each to be decision variables. Thoughts on scalability? That's a great question. So that's why we focused, I just mentioned it at the end, we focused on this issue of reducing the number of optimization problems that need to be solved, because if you were to use this in real time, the utility would be calculating these safety limits and sending them to the aggregator in real time, ideally like every 5 minutes or something. And so you need to make that optimization problem efficient. And if you're solving 2n optimization problems where n is the number of buses in your network, it could get really big. But a lot of the problems are redundant, because if you trigger a problem at one bus, you'd have a problem on another bus. So how do you effectively remove those problems is an important question. So Stephanie looked at that to some extent in this paper. And in the paper by Dan Molson and Lena Roll, they also, for a different problem, but a related problem, they looked at this as well. And then how do you account for impedances of low voltage lines and secondary transformers? So we're stall systems where there are small, and safety optimization is at the medium voltage level. So the current version of this system is, or of this problem, is just for a balanced three-phase network, but we're going to look at unbalanced three-phase power flow, so it could apply to any sort of system. But we don't have restrictions on the type of network, really. It's just that the current model doesn't include all the intricacies of the network. Like, we're not explicitly modeling the transformers. We're using a per unitized equivalent network. But I think you could do it. It just, again, would make the optimization problem harder to solve, and then you run into computational complexity issues. Okay, David's asking, could you share experiences from real power? When somebody types a new question, the whole window shifts. Could you share experiences from real power systems embracing similar kinds of coordination between distribution system operators and third-party companies? So I don't have direct experience. I've just heard a lot about this from my industry collaborators. There's a lot so in the US, there's some states that allow third-party aggregators and some states that don't. It's about a 50-50 split. So where we are in Michigan, we're at the University of Michigan, third-party aggregators aren't allowed. So if any type of coordination were to happen, a utility company would have to do it. But the utility companies here aren't so interested in this because they don't consider it part of their core business model. So we sort of lag behind the parts of the country where third-party aggregators are allowed to operate. But there's a lot of issues where it's not clear who needs to coordinate with who, because the aggregators are mainly talking to the market operators, the ISOs. But they're using resources at the distribution level and therefore affecting what the utility sees for flows in the network. So I think we're just still figuring it out. So in this work, we're really trying to propose different ideas where you could have some level of coordination. It doesn't have to be that the utility sends limitations to the aggregator. It could be the other way around, where the aggregator has requests and the utility actually manages them out to the consumers. And we have other papers that look at that architecture, and there's certainly trade-offs associated with it, but it's sort of a matter of figuring out who's willing to take on what role and who has what information, and what information are they willing to share with the other. I think I've got 1 more minute. So Dan's asking 2 questions. We considered the 2 norm and the 1 norm. Another thing we could do is use a weighted norm. Geometrically, this corresponds to expanding an ellipse rather than a ball. Did you consider this or other constraint formula? No, we didn't. We were just trying to understand for these 2 options how conservative the solution was going to be, but we haven't considered other options. There's a lot of open questions about how to formulate that problem correctly. We worry that it's too conservative, not just a little too conservative, but too conservative. And did you ever run into cases where your solver returned a low voltage power solution as opposed to a high voltage power solution? That's a really interesting question. So we run it multiple times with different initializations because it's a non-convex problem. I don't actually know if Steph ended up encountering some of these other solutions and throwing them out until she got something that she thought was a realistic solution. But that's something I can check with her about. Yeah, so I know that there's more questions, but I'm going to stop there in the interest of time, and I'll answer them in the chat box, or in the Q&A window rather. So thank you very much for your attention.